right, let's dive right in. We're going to talk about some of the most important particles in the entire universe, the ones that literally hold everything together. They're called bosons, and they're kind of the ultimate social particles. And by the end of this, you're going to see how their incredibly strange quantum behavior leads to effects you can literally see with your own eyes. But let's start with a mystery. Picture a liquid, cooled down so far it's just a whisper away from absolute zero, the coldest temperature possible. Now, you'd expect it to just sit there, right? But instead, it starts to crawl. It climbs right up the walls of its container and spills over the top, completely defying gravity. This isn't science fiction. It's a real thing called superfluidity. So how on earth is this possible? Well, the answer, believe it or not, is bosons. To solve this crazy puzzle, we have to back up a little. We need to understand that every single particle in the universe, and I mean every particle, belongs to one of two teams. There's Team Fermion and there's Team Boson.
And let me be clear, this isn't just some convenient way we categorize things. It is a hard, fundamental rule of quantum physics. Every particle we have ever discovered fits into one of these two boxes. There's no middle ground, no exceptions, it's one or the other.
So what's the difference? Well, it's pretty much everything. Think of fermions, that's the stuff that makes up all matter, like electrons and quarks, you and me. Think of them as the ultimate loners. The rules of physics say they absolutely cannot share the same quantum state. They need their personal space. But bosons, they're the complete opposite. They are the party animals of the universe. They love nothing more than to all pile into the exact same quantum state. And this one's social behavior, it's the key to everything. So what actually decides if a particle is a loner or a party animal? It all boils down to one single fundamental property called spin. Now, it's not literally spinning like a tiny basketball, but you can kind of picture it as this built-in, intrinsic angular momentum. And the value of that spin is what dictates which team it's on. Okay, so here's the official definition. A boson is any particle that has an integer value of spin, a whole number, like 0, 1, or 2. That's it. Fermions, on the other hand, have these weird half-integer spins, like 1/2. And the name boson, it actually comes from the physicist Sachendra Nath Bose, who, working with Einstein, figured out the rules for how these social particles behave. And this quote just perfectly captures the results of that integer spin. The laws of quantum mechanics literally permit an unlimited number of bosons to occupy the exact same place, at the exact same time, in the exact same state. It's like they have no concept of personal space at all, which is something that's totally forbidden for matter particles like electrons. So who are these fundamental bosons anyway? Let's meet the all-stars, the key players in the standard model of particle physics that are responsible for, well, pretty much all the forces we see in the universe. Here's the lineup. You've got your force carriers, which all have a spin of 1. There's the photon, which carries the electromagnetic force. That's light, electricity, magnetism. Then you have gluons, which carry the strong force that glues atomic nuclei together. And the W and Z bosons, which handle the weak force. And then there's the odd one out, the Higgs boson. It has a spin of 0, and it's not a force carrier in the same way. Its job is to give other fundamental particles their mass. But here's where it gets really cool. Bosons aren't just these tiny elementary particles. You can actually build bigger ones out of fermions. And the rule for how to do it is shockingly simple. See, when you start combining particles to make bigger things, like an atom, its team, whether it's a boson or a fermion, depends entirely on the smaller parts it's made of. All you have to do is a little bit of counting. And this is the rule. It's just simple math. If you take an even number of those loner fermions and you stick them together, the new composite particle you just made acts like a social boson. Their half-integer spins just add up to a nice, clean whole number, and suddenly the whole group wants to party together. And this opens up a whole new world of composite bosons. Mesons are bosons. A deuterium nucleus is a boson. But the one I really want you to focus on, the key to our whole mystery, is the helium-4 nucleus. It's made of 2 protons and 2 neutrons. That's 4 fermions total, an even number. So the entire helium-4 atom behaves like a boson. Okay, we have all the pieces of the puzzle now. We know what a boson is, we know they like to party, and we know a helium-4 atom is one of them. So let's bring it all back home and finally solve the mystery of that gravity-defying liquid. So that liquid climbing up the walls? Yep, That's liquid helium. Specifically, liquid made of those helium-4 atoms. And as we just figured out, helium-4 atoms are composite bosons. This is the crucial clue.
Here's how it all goes down. You take these helium-4 atoms and you cool them down, way, way down, stripping them of almost all their energy. Now, because they're bosons, they don't have to stay apart. Instead, they all start to drop into the single lowest energy state available, all together. Trillions of them. They essentially lose their individual identities and condense into what's called a Bose-Einstein condensate. They start behaving like one single giant superatom. And this bizarre quantum entity, that's our superfluid. And that is the absolute key takeaway here. This weird abstract quantum rule that particles with whole number spins can all pile into the same state, it isn't just some footnote in a physics textbook. It creates real, macroscopic, mind-bending effects that we can actually see and measure in our world. Now, we've seen how bosons carry the electromagnetic force, the strong force, and the weak force. But you might have noticed there's a big one missing from that list. What about gravity? Well, our best theories predict that gravity also has a force-carrying particle. It's called the graviton, and you guessed it, it's theorized to be a boson with a spin of 2. So if gravity, the force that sculpts galaxies and holds our feet to the ground, is also mediated by these supersocial particles, it just makes you wonder, doesn't it? What other absolutely bizarre large-scale quantum effects, just like superfluidity, might gravity be hiding from us in plain sight?